So this is the solution to homework set number 2 for ECE 320 Electronics 1. The first question is, why does resistance of silicon decrease as temperature goes up? Well, as temperature goes up, I get more thermal electrons. More thermal electrons means more thermal holes. More charge carriers means less resistance. So resistance goes down as temperature goes up. On problem 2, it asks, what doping of boron do you need to make a 1000 ohm resistor? So the dimensions are in 0805, 3.2 millimeters by 1.6 by 0.95. The resistance is resistivity times length over area. I know the resistance is 1000 ohms. I know the length. I know the area. So the resistance must be 47.5 ohm centimeters. Whenever the resistivity is the conductivity, that's the number of charge carriers times the mobility times the charge per carrier. Solving, I get the number of carriers, which is the doping, is 2.6 times 10 to the 14th. That may seem like a big number, but you got to remember Avogadro's number is 10 to the 23rd. So one atom out of every 10 to the 9th is boron. Very few atoms, so it doesn't change the mechanical or the crystal behavior, but has a big impact on the resistance. It's now a 1000 ohm resistor. Problem 3 is just plug into equations. This is the resistance of a thermistor. It's the one that we typically use in lab. Your beta or B number is 3905. And T here is in Kelvin. Kelvin plus 273 is centigrade. So at 0 degrees Fahrenheit minus 17 degrees Celsius plus 273 gives you the temperature in Kelvin. Plug it in. I get 8992 ohms. I warm up to 98.6, 605 ohms, 103, 545 ohms. So if I can measure resistance, I can tell you temperature. Problem 4 is for a PN junction. If you have a PN junction, there's a couple ways to explain why current flows one way but not the other. One option is P to N, I'm using majority carriers. Majority carriers means a high number of carriers, meaning low resistance. So low resistance P to N. N to P is minority carriers. That'll be typically 10 to the 6, 10 to the 8 times fewer carriers, meaning 10 to the 6, 10 to the 10 times higher resistance. If there just aren't very many minority carriers, that means the resistance is very, very high. So low resistance P to N, high resistance N to P. A second way to explain it is there's a depletion zone in the diode. If I apply voltage P to N and I squeeze the depletion zone down to 0, which is about 0.7 volts for silicon, it conducts. The other way around, the depletion zone just gets bigger. A third explanation is there's a potential energy barrier, about 0.7 volts. If I give the electrons enough energy, say 0.7 volts, they can flow. Less than 0.7 volts, they don't have enough energy to overcome the potential energy barrier. Any of those are acceptable. Problem 5 is a graphical solution. If I have this circuit, I can find the current and voltage by drawing a graph. The blue line is the VI characteristics for diode. That's this exponential. The orange line is when the current is 0, I'll have 5 volts across the source. That's this point. If I short the diode, make it 0 volts, I'll have 5 volts over 100 ohms, 50 milliamps. 2 points defines a line. The intersection is when I satisfy the characteristics for the voltage and resistance, and I satisfy the characteristics for the diode. I'm right here. About 0.8 volts, 42 milliamps. Problem 5b is solve these two equations. I'm going to have two equations for two unknowns. One equation is the diode equation. Given VD, I can find ID. The second equation is the circuit. So the current is 5 minus VD over 100. Gives me two equations, two unknowns. And MATLAB I can solve. I'm going to first guess the voltage, VD. Given VD, I can find ID. Given ID, this should be 0. Instead of making a 0, just make an error. And J is the error squared. The voltage that minimizes J will be the solution. For MATLAB, I can try that using the function fminsearch. I'm going to minimize this function with the original name cost. My initial guess is 0.7 volts. And it iterates and finds out that the answer is actually 0.7931 volts. And here's the sum squared error, almost 0. So the solution for MATLAB is 0.793 volts and 42 milliamps. In Circuit Lab, I can solve. build the circuit using a 4004 diode, and I get 0.751 volts, 42.4 milliamps. And I can also build it in lab. So these breadboards that you have, the outer rail is 5 volts. So the red one's 5, the red or blue is ground. That's the plus minus. I'll take a resistor from the 5 volts, here's my 1K resistor, to a diode to ground. That line means the direction of current flow. That's the arrow for the diode. And this is a brown, black, brown, brown, black, black, brown resistor, 1K. What I found is 0.774 volts and 42.6 milliamps. So comparing, notice I have 5 different answers: the graphical, numeric, ideal diode, simulation, and lab. They're similar, but they're all slightly different. That's typical when you have diode circuits. Each one takes a slightly different assumption. The actual experiment is what you care about. This is the actual current. The simulation uses mathematical model. The ideal diode uses a simplified model. Nothing in nature is going to be nice and round like 0.7000. Numerical solution uses a different model. So again, you're going to have similar answers. The ideal diode model, note that it's pretty close. The ideal diode circuit was easy to analyze, and the answers aren't too far off. Typically, what makes sense is use the ideal diode model to approximate the answer. If you want to get a more accurate answer, go to Circuit Lab or build it. Problem 8 to 10 is similar. Here's a circuit with 3 diodes. The equations would be given V1, V2, V3. I can find the current through the diode. For diode 1, the voltage across it is V1 minus V2, so that's the voltage I plug in here. Diode 2 sees V2 minus V3, plugs in here, and diode 3 sees V3 minus 0. Then the voltage node equation at node 1, current left, down, 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 as to 0. This current is ID1. At node 2, it's minus ID1 plus ID2 plus the current left plus the current right. Node 3, it's minus ID2, the current up, plus ID3, current down, plus the current right, equals 0. And MATLAB I can solve. Here I've got really 3 equations, 3 unknowns, but they're hard to solve, they're nonlinear. That's where fmin search comes into play. I'm going to guess my voltages, V1, V2, V3. From the voltages, solve for the currents. Then I'll sum the currents to 0. If I guessed wrong, they won't sum to 0. That's my error 1, error 2, error 3. Return the sum squared error. Let fmin search find what voltages minimize the sum squared error. It says the answer is 2.08, 1.40, 0.72 volts. With an ideal diode, I'd assume all 3 diodes are on. If they're on, then this is 0.7 plus another 0.7 plus another 0.7. Assuming all 3 diodes are on, I get 0.7, 1.4, 2.1 volts. Then I just have one equation, one unknown. Solve for the current through the diode, I get 4.5 milliamps. And let's see where we at. Oh, in Circuit Lab, I can simulate, and you get not exactly 0.7, 1.4, 2.1 volts, but close. In a lab, you can build it. So here's the 5 volts going through the 100 ohm resistor. There's the first diode, second diode, third diode to ground, and a couple of resistors tapping it off. So the net result is the voltages V1, V2, V3 that I solved numerically versus an ideal diode versus the simulation versus lab will be similar, but slightly different. Again, they all make slightly different assumptions. So that's homework set number 2 for ECE 320.